students, today we will see the nature of the carbon and halogen bond. So in carbon and halogen bond, the halogens are more electronegative, hence it has a partially negative charge and carbon is having partially positive charge here, and the paired electrons present here, they move towards or they are towards the halogen atom, hence they are the bond here, it is a polar bond and these molecules are polar molecules. Let's see the different kinds of carbon-halogen bond here, that is a bond between carbon and chlorine, bond between carbon and chlorine, bond between carbon and bromine, and the bond between carbon and iodine. So here when we go down the group, the size it decreases, hence the bond length of carbon and fluorine is the least and the bond length of carbon and iodine is more here. So when we see the bond strength of carbon and fluorine, it is more than carbon and chlorine, and the bond strength of carbon and chlorine is greater than carbon and bromine, and this is greater than carbon and iodine. So the bond strength it is higher for carbon and fluorine. Next, if we see the dipole moment, the carbon and chlorine it is higher than the carbon and fluorine, and this is higher than carbon and bromine, and the carbon and iodine is having less dipole moment. Now let us study the methods of preparation of alcohols. So the alcohols can be prepared by different methods, that is they can be prepared from alcohols, they can be prepared from hydrocarbons, they can be prepared from alkenes, and also by halogen exchange method. So first we will see how the haloalkenes are prepared from alcohols. So this method of preparation of haloalkenes from alcohols is most widely used method in the laboratory for the preparation of haloalkenes. So the alcohols are that class of compounds having the general formula ROH, where R is the alkyl group and OH is the functional group. So the functional groups are more reactive here and they are responsible for the reaction. So OH here it is replaced by the halogen on reaction with either an halogen acid or with a phosphorus trihalide or phosphorus pentahalide or with a thionyl chloride. So here the reaction will be between ROH with either with the halogen acid or with the phosphorus trihalides or with the phosphorus pentahalides or with the thionyl chloride. Alcohol, when it is reacts with the halogen acid, here the OH is replaced by the halogen and we are going to get the haloalkane, and there is a formation of the water which is a living group here. Haloalkenes can be prepared from alcohols by the action of the halogen acids here. So here primary alkyl halides and the secondary alkyl halides can be prepared by the action of the halogen acids in presence of the anhydrous ZnCl2. We are going to get the alkyl halide, but for tertiary alkyl halides, as the tertiary alkyls are very reactive, they doesn't need the anhydrous ZnCl2 here. In the room temperature, simply by shaking a tertiary alcohol with the halogen acid, we are going to get the tertiary alkyl halide here. So the action of this ZnCl2 here, it acts as a catalyst. So this ZnCl2 it is a Lewis acid. So it coordinates with the oxygen and it helps in the breakage of the carbon and oxygen bond, and it forms the carbocation, which will give us the haloalkane here. Bromoalkenes can also be prepared from alcohols here. So an alcohol, when it reacts with the hydrobromic acid, that is 48% of the hydrobromic acid in presence of the concentrated H2SO4. Here the concentrated H2SO4, a small amount of concentrated H2SO4 is used, and we are going to get the bromoalkenes, and the water is the living group here. If I take an example here, that is ethyl alcohol, when it reacts with the hydrobromic acid in presence of concentrated H2SO4, and when we heat it, we are going to get the ethyl bromide and the water. So HBr, it can also be prepared in situ by the action of H2SO4 with either the KBr, potassium bromide, or with the sodium bromide. We can prepare the HBr in situ, that is in the reaction only we can prepare the HBr. So here the HBr used, hydrobromic acid used is 48% hydrobromic acid is used for preparation of bromoalkenes. Iodoalkenes, they can be obtained by the heating of alcohol with the constant boiling hydroiodic acid, that is of 57% hydroiodic acid. When it is reacted, we are going to get the iodoalkenes. If I take an example here, ethyl alcohol, when it reacts with the hydroiodic acid, we are going to get the ethyl iodide here, and H2O is the living group. So hydroiodic acid, it can be prepared in situ, in the sense in the reaction only by the action of phosphorus acid on potassium iodide. Halogen fluorides, they are less reactive, hence we cannot prepare the halogen fluorides by this method. Now we will see the order of reactivity here. So the tertiary haloalkenes are more reactive than the secondary, than the primary. So the order of reactivity of alcohols is: tertiary alcohols, they are more reactive than the secondary alcohols, and the secondary alcohols are more reactive than the primary alcohols. If we see the order of reactivity of these halogen acids on alcohols, the hydroiodic acids, they are more reactive than the hydrobromic acids, and then these hydrobromic acids are more reactive than the hydrochloric acids. So the next, by using the phosphorus halides. So in alcohol, when it reacts with the phosphorus pentachloride, we are going to get the chloroalkane and phosphorus oxychloride and a hydrochloric acid. So alcohol, when it reacts with the phosphorus trichloride, we are going to get the chloroalkane with the phosphoric acid. So let me take an example here. Ethyl alcohol, when it reacts with phosphorus pentachloride, we are going to get the chloroethane, phosphorus oxychloride and a hydrochloric acid. And when ethyl alcohol reacts with the phosphorus trichloride, we are going to get the chloroethane and the phosphor H3PO4 here. So here in PCl5, one of the halogen is replaced here from the OH group. So I get CH3, CH2, Cl, and in the other 4 chloride atoms are remained here. So 3 atoms are attached to phosphorus here, and we are going to get a phosphorus oxychloride. The remaining one will attach to one of the hydrogen, and we are going to get the hydrochloric acid. So this is the one of the method for the preparation of the chloroalkenes. Bromoalkenes as well as iodoalkenes can also be prepared by the action of phosphorus tribromides or the phosphorus triiodides respectively with the alcohol. As phosphorus tribromides and phosphorus triiodides, they are not stable, they are prepared in situ. That is, in the reaction only they are prepared. That is, when the reaction with the action of red phosphorus on Br2, we are going to get the phosphorus tribromide. In the same way, when the action of the red phosphorus on iodide, we are going to get the phosphorus triiodide here. So when alcohol is reacted with the phosphorus tribromide, we are going to get the bromo, ethane and phosphorus acid. Similar way, when ethyl alcohol reacts with phosphorus triiodide, we are going to get the iodoethane and phosphorus acid here. Next, we can prepare by the action of the thionyl chloride here. So the chloroalkenes, they can be prepared from alcohols by refluxing alcohol with the thionyl chloride in presence of the pyridine here. So alcohol, when it is refluxed with the thionyl chloride in presence of the pyridine, we are going to get a chloroalkane, SO2 and HCl, which are in the gaseous form. Hence, this is the best method of preparation of the chloroalkenes. So, if I take an example here, ethyl alcohol, when it is refluxed with the thionyl chloride in presence of pyridine, we are going to get a ethyl chloride and SO2 and HCl, which are in the gaseous form. So, this is the best method for the preparation of chloroalkenes. Thank you.